All right, so let's look at the pendulum. No, the springs. The springs. We did several different experiments with the springs. And so if I were recording in a lab notebook, you know, what we gleaned from our little laboratory experiments, let's see, there was a group that varied what? The amplitude? And what did we notice when we varied the amplitude? Do you remember? What did it look like? Okay, so what can we say about the period and the amplitude? Period is what? Independent? Of A, the amplitude. Okay. So then we varied what? What was the other thing that was easy to vary? Mass. So we had a group that varied the mass and measured the period. And what did you get? Something that looked like, or I really wanted it to look like this. Ooh, what's that relationship look like? How is the period related to the mass? The square root of the mass. That's right. The period depends on the square root of the mass. All right, so let's see. If you notice, when we did the pendulum up here, we came up with the fact that the period must be related to the square root of the length. And if you look at our final equation for the period, did I go back full circle? See, the square root of L is in there? I'm trying. Okay, so let's look at the spring. So when the spring is oscillating back and forth, what is the restoring force? What force, when you've got the spring stretched way down here, away from its equilibrium position, what force is pulling it back to the equilibrium position? The spring force. That's right. So when our spring force is a maximum, we have a maximum MA. Does anybody remember the spring force equation? 1/2 kx squared is the energy stored in the spring. Remember, it looks like the other energy equations, like 1/2 mv squared, 1/2 cv squared, things like that. So the force, though, was kx. So that would be kx max equals m a max. All right, so let's do some substitutions into x max. What is the maximum displacement called? When something is going up and down and up and down and up and amplitude. That's right. So there's A for amplitude. What about the maximum acceleration of an object that's oscillating back and forth? A omega squared? What doesn't matter? Amplitude. Did we find on Thursday last week that the amplitude didn't matter? Yay! So cool. All right. So then what is the angular speed or angular frequency of a spring? That's right. Square root of K over M. And y'all like a box, so we'll throw a box around that. So omega is your angular frequency, still measured in radians per second. Spring constant is measured in newtons per meter, and in this class we should measure mass in kilograms. There you go. All right, so using the same model as before, since omega is equal to 2 pi over period, then period is equal to what? 2 pi over omega. So the period for a spring would be what? 2 pi over the square root square root of K over M, but that's kind of oogly. What do we want to do? Let's flip over the square root business. M over K. And y'all like a box, so I'm going to write it down here so it'll be nice and pretty. The period of an object oscillating on a spring is equal to 2 pi square root of m over k. And we'll throw a box around that. Okay, so the one thing I didn't address yet was, did we have two groups that had two different springs? One had like a stretchy spring and one had a stiffer spring. Okay, and you guys varied the mass. You kept the amplitude the same, and you made the same changes with your mass. So we had the period in seconds, and we had the mass, and I think y'all probably put it in grams, but I'm going to throw it in kilograms to be a good teacher. And then we had the second graph for the other group, and the mass and the kilograms. And so there was a stretchy spring. The stretchy spring, tell me about its K constant. Was its K constant low or high if it was real stretchy? A stiff spring has a what kind of a high? So a stretchy spring would have a low K constant, and then we had one that had a high K constant. The one with the low K constant, didn't it have like a maximum period of about 1 second? And if I use the same exact scale for both of these, the one with the high spring constant, didn't it have about half of that? Now we've already discussed that this looks like a square root function. So how is the K constant? We've got a low K constant, we get a high period. We have a high K constant, we get a low period. What's the relationship between the K constant and the period then? Directly, indirectly? It is indirectly. And look, there is our K constant living in the denominator. If it goes up, period's going to go down. So that was the purpose of doing those two different graphs, to show you the relationship. And it's still inside the square root function. So let's summarize just a bit so that when I turn you loose, you have something to go on here. So the angular frequency for a pendulum is the square root of G over L. The period for a mass on a pendulum is 2 pi square root L over G. The angular frequency for a mass oscillating on a spring is the square root of the spring constant over the mass. The period is 2 pi square root of m over k. And the same equations for maximum velocity, which was what? A omega. And the maximum acceleration, which was a omega squared, still hold true. This is still oscillating motion. So we can still use these guys together. The goal was just to have you do a lab where you got to derive these relationships, or at least look at the relationship